Engineering acoustics is a broad field of engineering. The images shown here cover just a small part of engineering acoustics applications. How do we design a space, such as the 500-seat lecture theatre in the Advanced Engineering Building at the University of Queensland, so that people sitting in all of the seats in the room are able to clearly hear what is being said by the presenter? What do we put on the floors, ceiling and walls? Do we need to hang anything from the ceiling to help improve the acoustics? How many speakers are required and where should they be placed? How do we make measurements of the noise from an item of machinery? Is the noise generation uniform in all directions, or is it louder in some direction than others? How much noise is generated at a mine site? And how does that sound propagate from the site to the surrounding environment? If the noise levels are too high, what can be done to reduce these levels at different locations? Aircraft can make a lot of noise, and that noise propagates out into the atmosphere. Again, we may be interested in what can be done to reduce the noise level being generated, or in how that noise propagates to a location on the ground. The fans at a sporting venue can generate a lot of sound power that can propagate out into the community. How do we estimate how much sound power could be generated? What can we do to limit how it propagates? And what would be the noise level at different locations outside the venue? Engineering acoustics has applications in many aspects of industry, and it can affect the community. Sound can vary in amplitude and in frequency. We'd normally think of acoustics as sound propagating through air, but we can also have sound propagating through other media, such as water or solid materials. Formally, acoustics is the study of propagation of stress waves through a medium. Consider first acoustics based on the amplitude of the sound, that is, how loud is the sound. When the amplitude is low, the speed of propagation of the stress waves through the medium is constant. For air at standard temperature, sound waves of typical amplitudes travel at a constant speed of about 340 meters per second. We call this linear acoustics. Linear because we can use ideas like superposition of two sound waves, and the resultant is just the addition of the two individual waves. If the amplitude is higher, we can get the situation where the waves travel at a speed that's dependent on the amplitude of the sound. An example is a blast wave or a shock wave of very loud amplitude that can start travelling at speeds in excess of the speed of sound. I guess then that the speed of sound is a misnomer in this case. As the blast wave propagates and decreases in amplitude, the speed of propagation slows until it reaches the standard speed of sound. We call this area of acoustics nonlinear acoustics. That was thinking about the amplitude of the sound. We're also interested in the frequency of sound, the spectral nature of sound. Again, the study of stress waves propagating through a medium. A typical human ear, in good condition, will be able to detect sounds at frequencies from around 20 Hz all the way up to about 20 kHz. This frequency range of acoustics we call sound, or noise if it's unwanted sound. Sound at frequencies too low to be detected by a human ear is referred to as infrasound. Human ears may not be able to detect infrasound, but the human body may be able to, and it may be affected by it. For example, there's debate within the scientific and general community about the effects of very high amplitude infrasound on humans, and whether and under what circumstances prolonged exposure can lead to health problems. And sound at frequencies too high to be detected by humans is referred to as ultrasound. An example of an application of ultrasound is in identification of defects in structures, which I'll discuss a little more soon. A large part of engineering acoustics is noise control. We want to make sure that noise is not causing damage or annoyance to people, or damage to infrastructure. Acoustical engineers are, or should be, involved in the design of products and processes. If we can be involved at this stage, we can ensure that the devices and processes meet the acoustical needs and comply with any regulations. So this is proactive noise control. It's best to pick up the noise issues in the design process, but acoustical engineers are often called in to reduce an existing noise problem. We refer to this as reactive noise control. The acoustical engineer needs to gather information, usually in the form of level and spectra of the noise, identify what is causing the problem, identify possible solutions, implement the best solution, and test again to see if the problem has been resolved. Acoustics is also used as a diagnostic tool. Non-destructive testing is one application. I mentioned ultrasound as a potential tool for detecting flaws in structures. This might involve exciting a part of a structure with ultrasound at one location and measuring the propagated sound at other locations. Analysis of the signals may allow us to make some conclusions about the structural integrity of the component. For example, we might do this for the structure without defects and then do it for one with defects. We can then potentially identify the nature and location of the defects. Non-destructive testing may be used in this way for quality control. We test our products to ensure that they do not have defects. We can also use acoustics to monitor the condition of a machine or process. For example, we might measure the noise being generated by a machine and note that there's an increased noise being generated in a particular frequency range. We may then be able to track down what could be causing that noise, for example, a failed bearing, and use this information to inform the required maintenance or repair. We may also use this type of technique to help us decide when to do the maintenance so that we do it before there's a major failure. The best way to think of acoustical problems is in three processes. The first is the source. So what is it that's generating the noise? The next is the path. And along the path we may have attenuation, distortion, or amplification of the sound. And the third is the receiver, where we're receiving the sound, and that's usually our ear. So if we start off with a certain spectra of sound, so this is a spectra of sound represented by the level in decibels vertically and the frequency in octave bands along the horizontal axis. And we have different amounts of sound in different octave bands. So that's the noise that's generated at the source. By the time it reaches the receiver, after it's gone through this path, where there may be attenuation, distortion, and amplification, the spectra may be changed in terms of how there is in different octave bands, and the overall level may also be changed. So both the level and the spectral content are important in acoustics. Let's look at noise control strategies, and let's start with the source. We'll always start with the source. The first thing we might try to do is to modify the source. Can we modify it to reduce the sound that it's generating? For example, if we have a mechanical system, we may be able to do things like minimize the acceleration. So here's an example of cans being dumped into a hopper. They're coming up a conveyor and going down into the hopper here. And when they hit the hopper, the more kinetic energy they have, the more sound could potentially be generated. So if we put some flaps along the way to reduce the final fall height, we can reduce the noise being generated. So the rubber flaps to reduce the mechanical shock. We can also look at something like spur gears, which might be generating sound. And if we replace the spur gears with helical gears, we can potentially reduce the sound that's being generated. The next thing we look at is the path, where we've got the attenuation, the distortion, and the amplification. So we then approach trying to modify the transmission path in order to reduce the noise at the receiver. An obvious thing to do is to relocate the source or relocate the receiver, so we're changing the path between the source and the receiver. Another option is to interfere with the path. And a good example of interfering with the path are roadside noise barriers. So the barriers are there such that the source of the noise, which is the cars on the road, and the receiver might be a residence on the other side of the barrier. The noise propagation from the source to the receiver is interfered with by the noise barrier. Then we move on to the receiver. And this should only be when all else fails that we do something at the receiver. And then it may be necessary to modify the receiver. And the obvious thing to do here is to provide hearing protection for people. But importantly, this is the last point that we aim for. We really want to avoid this at all costs if we can. So in summary, a noise problem can be thought of as a source, a path, and a receiver. And along that path there's that attenuation, distortion, and amplification. We always start looking to solve a noise problem in this order. We start at the noise source. Can we reduce the noise being generated at the source? Then we move on to the path. Can we amend the path such that the noise which reaches the receiver is reduced? And then, if all else fails, we ensure that you protect the receiver, potentially with hearing protection.